In this video you will learn how to derive the two basic forms of the voltage divider rule, which we have seen in the last video, based on the concepts of current equality and also on Ohm's law in a series circuit. And by the end of this video you will know the two formulas that you can use to calculate unknown voltages in a circuit, and you will also know where they come from and under which circumstances and which conditions they can be applied. And you will also be able to identify situations where they may not be applied simply because the basic assumptions are violated in one form or the other. And finally, as always, there's going to be a summary of the most important facts from this video at the end for you. And my name is Andreas from the Fearless Engineer, and here we go. Let's quickly review the voltage divider circuit, which we have looked at in the previous video on the voltage divider in a nutshell. It's a very simple circuit with a perfect voltage source on the left, which provides us with 5 volts of total voltage. We have 2 resistors which are placed in an unbranched circuit, and across these resistors we have a voltage drop of 1.67 volts with the upper one and 3.33 volts with the lower one. And if you look at this ratio of voltages versus via the ratio of resistance values, you can see that the ratio of resistances is directly proportional. It's even identical to the ratio of voltages. So 100 by 200 is identical to 1.67 by 3.33. And depending on which quantities are known and unknown, let's say you do not have the voltage drop across the upper resistors, but you have been given the total voltage drop, you can choose one variant of the voltage divider. And if you are not aware of the total voltage drop, but you have the voltage drop across the second resistor and are again looking for the voltage drop across the first resistor, you can use another variant of the voltage divider. Now in this video we will derive both variants of the voltage divider from scratch using some of the concepts we have been talking about in previous videos, such as current equality and also Ohm's law. Let's start with the first variant. In this variant here, we have not been given the total voltage of the source, but we have the voltage drop across the second resistor here. U2 is given to us. Also, of course, we have the individual resistance values, and we are looking for the voltage drop across the top resistor here. And the idea of computing the formula for this voltage divider situation is by exploiting the current equality in an unbranched circuit, which means in a circuit where no junction points exist, all the charges which leave one of the terminal of the batteries must arrive at the second terminal of the battery. They cannot be lost. And this means, as the current is not branched away, there's no junction point, the current flow is identical for both resistors, which means the total current flow is identical to the current flow through the first resistor, is identical to the current flow through the second resistor. And now we can replace these individual currents here with Ohm's law, which states that the current flow is identical to the ratio of voltage drop and resistance value. And if we simply enter these equations here, we can produce all the variants which we like. We can simply say, okay, if we do not possess the total amount of voltage drop, but we have one voltage drop given from one of the partial resistors, let's scrap this one out here on the left and keep the two components on the right side and simply solve them for either U1 or U2, depending on what we are looking for and what we have been given. And this gives us the left equation or the right equation. With the left one we can compute the voltage drop across the top resistor, and with the right one we can compute the voltage drop across the bottom resistor, which is simply the product of voltage drop across the first resistor multiplied with the ratio of resistance value across the voltage drop across the voltage we are looking for, which means the resistance value for the resistor we are looking for divided by the resistance value of the other resistor, and vice versa for the situation where you are investigating the voltage drop across U2. So this basically, even though we have two equations, this is the first variant of the voltage divider. And in the second variant of the voltage divider, we have been given the total voltage of the source. We do not have the voltage drop across the lower component, and we are still looking for the voltage drop across the topmost component. And if we take all these factors here into consideration, nothing has changed with the circuit, so we can still exploit the equality of current running through all parts of the circuit. And this is what we're going to do on the next slide. And as you can see here, we can first, in the first step, compute the total resistance of this setup here by simply summing up the individual resistance values. So this is the first thing we need to do. Obviously, if you have not watched the video on how to compute the resistance value of joint resistors, you might want to do this first to understand why this is permissible. But intuitively, you can look at the current running through this unbranched network, and obviously each resistor places a certain amount of resistance in the path of the electrons, and if you place two resistors directly behind each other, the resistance simply adds up. And this is why, in a nutshell, we can assume that the total overall resistance of the series connection here is the sum of the two individual resistance values. But we will still make a video on the resistance of a series connection. However, if you apply the same formula as before, we can again say that the total current is identical to the current through the first resistor is identical to the current through the second resistor. Now we can replace these components, what has already been done, by using Ohm's law, and then we simply look at what's given, what's searched for, and as we are now given U total, we can keep it, and if we are looking for U1, we keep the left two components of the equation, and if we are looking for U2, we scrap the middle one and keep the left side and the right side, and this is what this leads to. So the voltage drop across the first component is simply the product of the overall voltage drop multiplied with the resistance value of the first resistor and divided by the sum of the individual resistance, or the sum of the individual resistances, which is the overall resistance we have computed in the first step. And the same can be done, of course, for the second voltage drop, U2. Now you have to be careful with this example here. It's looking very similar to the last one with one exception. You still have one resistor at the top and one resistor at the bottom, but now there's a third resistor which is connected in parallel to the second resistor. And if you apply the standard voltage divider as has been done here, second voltage U2 is identical to the first voltage multiplied with the ratio of the individual resistance values. You arrive at a voltage drop across U2 of 4.54 volts. And if you check this with the simulation results, you will find this here on the next slide. As you can see, the voltage drop is much lower. It's only at 2.727 volts. And the voltage drop across the topmost resistor is at 2.2273 volts. So the sum is still 5 volts, but the distribution ratio has changed. And this is because the current through the two resistors, the topmost and the bottom resistor, is not identical. The current through the first resistor is at 22.73 milliamps, but the current through the resistor number 2 is only at 13.64 milliamps, because the rest is flowing through this third resistor which has been placed in parallel. And this is a violation of the equations which we have set up in order to derive the voltage divider. This states this equality between I1, I2 and I total. This enabled us to arrive at the overall resistance value and also at the formula which we derived. But in this case, this is clearly violated. So in such situations, the standard formula gives us a wrong result. And one way to solve this is to use another formula which is called the loaded voltage divider, which is something we're going to look at in one of the next videos. So take care, pay attention to these situations where you have something connected, a load connected to your voltage divider. Now let's quickly summarize the most important findings from this video here. So first is, depending on which quantities are known and unknown, the shape of the voltage divider must be adapted accordingly. Just cross out the parameters which you do not need and enter those and solve for those which you are looking for. Then second point, both voltage divider rules, they can be derived from the current equality of resistors, which are connected in series, in combination with Ohm's law to introduce the parameters which you are looking for. And then in general, the following applies. The total voltage drop across a series circuit or components connected in series is divided according to the ratio of the individual resistors. So if you know that one resistor is double the size of the first one, which has been placed in series to it, you know that also the voltage drop will be double in size in relation to the first one. But you have to heed caution in cases where the current equality is violated, just as we have looked at in the previous example. In this situation, the standard voltage divider cannot be applied, and instead you must use the so-called loaded voltage divider, which we will take a look at in the upcoming video. That's all for now. If you have any questions, drop me a comment in the comment section down below. And as always, I wish you a nice day. See you next time here on The Fearless Engineer.